Hello, good day. My name is Gloria Lourdes Dimas Rivera, and I am a professor at the Faculty of Chemical Sciences, Universidad Autónoma de Nuevo León. Today, I will present our work titled NiWO3ZSM5 Catalysts for Selective Hydrogenation Esterification of Furfural to Bioethers. Introduction. Furfural is a compound obtained from lignocellulosic biomass through thermal methods such as pyrolysis and hydrothermal processes. Currently, it is a key precursor in the industry, particularly for producing solvents and fuel additives. Levulinate esters are versatile chemical feedstocks used as spices in the flavor and fragrance industry or as blending components in biodiesel. Furfural is first converted into furfuryl alcohol, and then furan-2-iomethyl-levulinate, FMP, is formed through alcoholysis, self-condensation of furfuryl alcohol. This can be achieved through transfer hydrogenation using a donor such as 2-propanol instead of molecular hydrogen. Active catalysts can be synthesized using metal oxides with acid-base properties and zeolites such as ZSM5. In this project, NeOWO3 ZSM5 catalysts with 10% Ni and varying percentages of WO3, 5, 10, 15%, were synthesized using 2-propanol as the hydrogen donor for the hydrogenation esterification of furfural. Catalyst synthesis. The catalysts were synthesized using the impregnation method. To impregnate WO3, ammonium metatungstate was dissolved in 70 milliliters of water. Then the ZSM5 zeolite was added and stirred while a 10% hydrochloric acid solution was added dropwise. The mixture was then dried at 110 degrees and calcined at 500 degrees for 4 hours. For nickel impregnation, a nickel nitrate solution was dripped onto the calcined material with constant milling. This solid was then dried at 110 degrees C and calcined at 500 degrees C for 4 hours. Catalytic reaction. The reaction was carried out in a batch reactor with 20 milligrams of catalyst, 2 millimole of furfural, 20 millimeters of isopropanol at 220 degrees Celsius under nitrogen atmosphere, 350 RPM, and for 5 hours. The products were analyzed using gas chromatography mass spectrometry. Characterization. The materials were characterized using the following techniques: temperature program reduction with H2, TPR-H2, scanning electron microscopy, SEM, X-ray diffraction, XRD, temperature program desorption of NH3, NH3-TPD, and N2 physisorption. Results: XRD, characteristic peaks of ZSM5 zeolite and tungsten oxide were observed. Nickel oxide peaks were also evident, with a decrease in the intensity of the peak at 43.27 degrees in the presence of tungsten. TPR, the 10-cent NO ZSM5 catalyst showed an intense signal at approximately 425 Zs for the reduction of nickel oxide. The 10-cent WO3 ZSM5 catalyst exhibited several stages of reduction of WO3 to W0. Bimetallic catalysts showed lower reduction signals with increasing WO3 content, indicating greater interaction between the metals. TPD, the 10-cent NiO ZSM5 catalysts displayed acid profiles at 235 and 511 degrees Celsius, which increased and slightly shifted in the 10WO3 ZSM5 catalyst. In bimetallic catalysts, signals at 520 degrees decreased with more WO3, indicating that WO3 covers the acidic sites of ZSM5. SEM and N2 physisorption. The morphology of 10-cent NiO 10WO3 ZSM5 showed particles ranging from 100 to 500 nanometers, with some larger particles covering a significant portion of the zeolite. This finding aligns with TPD results. The 10-cent NiO 15-cent WO3 ZSM5 catalyst with the highest metal loading showed superior textural properties, including increased surface area and microporosity due to the formation of new pores by metal oxides. Catalytic conversion. The highest conversion was achieved with the 10N9 to 10W3 ZSM5 catalyst, 41.24%, with a selectivity of 51.17% towards furan-2-iomethyl-levulinate. The highest selectivity for levulinate was observed with the 10IO5W ZSM5 catalyst, 76%, although its conversion was the lowest, 26.83%. The acidity provided by WO3 and the interaction between metals favor the selectivity towards LF2M, and this is corroborated by the catalyst with the highest WO3 loading, 10NiO15WO3 ZSM5, which showed good selectivity, 56.13%, but a relatively low conversion, 31.48%. Conclusion. The presence of NiO and WO3 on the surface of ZSM5 zeolite was confirmed, modifying the properties of the zeolite mainly by increasing the total acidity of the catalyst with WO3 content. TPR analysis demonstrated interaction between the metals, leading to easier reduction with lower H2 consumption. In catalytic tests, the highest furfural conversion was achieved with the 10-Envy ZSM5 catalyst, 41%, with a selectivity of 51% towards 2-methylfuran 2-iolevulinate, LF2M. The highest selectivity for levulinate was observed with the 10-NNIO 503 ZSM5 catalyst, 76%, although its conversion was the lowest, 27%. The acidity provided by WO3 and the interaction between metals favor the selectivity towards LF2M, and this is evident in the catalyst with the highest WO3 loading, 10-NiO15-DO3 ZSM5, which showed good selectivity, 56%, but relatively low conversion, 31%. Thank you very much for your attention, and I hope you enjoyed it. Best regards.